So in the last class we were discussing about this system, which is a coupled system. Coupled system means that it is also attracted by the electric field as well as the mechanical force or the electrostatic force is trying to pull the A plate up, and in that case we have already seen that this is the electrostatic force, right, half into epsilon r epsilon naught A divided by d minus y whole square into v square, and the elastic force or the mechanical force is ky as we know, correct, and at equilibrium these two forces will be same, and then we draw this force diagram where we can qualitatively explain that as we are going from y equal to 0 towards y equals to d, right, then the electrostatic force is increasing like that, like parabolically, whereas the elastic force or the mechanical force is increasing linearly. So there are multiple solutions, like more than one solution, and here you can see that it is actually crossing the elastic force and the electrostatic force is crossing over 2 points, and we have seen that as we go more and more towards y direction, right, y equal to more and more towards the y equal to d direction, then the electrostatic force is getting higher and higher. So the beam A, like the plate A, will be pulled in on the plate B, okay, and so this will snap on the substrate. Also we have seen that these different these different lines are for different voltages, right, and at some voltage where electrostatic force just touches over the mechanical force, at this point this is called pulled in voltage, above that electrostatic attraction is always higher than the mechanical force, so there is no chance that the beam can be again pulled back, right. So this is called pull in voltage, Vp, and this is the graph for Vp where it is exactly touching over the mechanical force, right. Okay, now we will see this condition, the stability condition mathematically, and then we will try to derive the equation, and then we will try to derive the expression for pulled in voltage as well as the minimum gap which it can transverse without minimum gap which it can deflect without actually snapping on the substrate. So for that, my electrostatic force Fe is equals to half into epsilon naught, it's called epsilon r epsilon naught A divided by d minus y whole square, right, into v square, and mechanical force, let us say I call it Fm, equals to ky, right. So where from I am getting that? I have already derived this expression here, right. So we know the electrostatic force is W by d, which is actually half Cv square divided by d minus y, because if the y is the deflection, then the gap between the top plate and the bottom plate is now d minus y, right, and then you write C also in the form of epsilon A by d, then you get d minus y whole square. Okay. Now you see the first condition that the beam can be in the like in the stable condition. The first condition is that the resultant force, let us say Fr is equal to F electric field or electrical force minus F of mechanical force will be less than 0, right, because we go to this previous graph and we see that while the electric force, like for the topmost graph, right, for the topmost curve, you see the electric force is always higher than the mechanical force. So once it gets pulled in, the top plate gets pulled in and it gets attracted towards the plate B and it starts moving, there is no point where the mechanical force can be higher than the electrostatic force. So in that case what will happen, that it will always snap in. So it should be less than 0, like the electrostatic force minus the mechanical force, it should be less than 0. So the mechanical force should be higher, then only it can pull the beam up. So we can write then that half of epsilon r epsilon naught A divided by d minus y whole square v square minus what is mechanical force, ky, minus ky is less than 0, right. Okay. Now another important point is here that if you see from the graph, then what is the stability condition? What is the stability condition? At this point, see, initially at the starting, let's say take the let's name this graph. So let's say this is V1, then V2, V3, which is also my VP, and then V4. So for V1 case, let's say for V1 case, what we see that initially the electrostatic force is higher than the mechanical force, right, and as the electrostatic force start pulling the plate A, then it starts to move towards the plate B. So y starts to increase, right, y starts to increase, and so y moves in this direction, and as it moves, then the mechanical force start increasing, and at this point A, electrostatic force and the mechanical force is same, right, and after that if it deflects more, then what happens, then the mechanical force is higher, right, mechanical force is higher and electrostatic force is actually lesser. So if I draw the resultant graph, then it will be something like that. The resultant force will be like electrostatic minus the mechanical force. It will be initially positive, while y equal to 0, then it will slowly go down, right, it will slowly decrease, and then it will cross over 0, right, it will cross over 0, and then it will go towards negative, because in this point the mechanical force is actually higher, right, it will go towards negative, and then it will reach a minima, and then above that it will again start moving upward, right, it will start again moving upward, because after that the electrostatic force is increasing even in higher rate than the mechanical force, right, and in that case it will start again moving up, and accordingly it will reach the B point where both the forces will be same, and after that it is like the electrostatic force is always will be higher than the mechanical force. So the resultant force in this region, actually the resultant force is actually going down, and it will go towards negative also, and after that it will reach a minima, and it will again start moving up, and while it reaches the minima, that is the pulling point, right, that is the pulling point where it reaches the minimum. Now while the resultant force is going down, that means what, that means the slope is negative, or delta Fr by delta y is less than 0. So this is my FR, electrostatic force minus mechanical force, and what I am saying that the resultant force will even go down, right, as we are increasing the y, and that is the region where the where we can tell where we can assume the beam is in stable condition, right. So as the FR is going down with y, delta FR by delta y also less than 0, that means it is negative slope, right, while y increasing resultant force is decreasing. Now what is delta FR minus what is delta FR by delta y? That is epsilon r epsilon naught a v square divided by d minus y whole cube, right, minus k less than 0. So that you can actually this is the FR expression, right, this is the FR expression, and in this expression I am doing just the first derivative. So if I do, then you get for this d minus y whole square, this 2 comes, and then I get d minus y whole cube below, and there also a minus comes, but there is also a minus y, so that minus minus becomes plus. So ultimately I get epsilon naught epsilon r epsilon naught a divided by d minus y whole cube into v square, right, from this term, and this is just k. Now what we know from pooling point? From pooling point I know that the electrostatic force and the mechanical forces are both are same, exactly same. That means my half of epsilon naught a by d minus y whole square into v square is equals to ky. Okay. Now if I now let's put this expression in the let's call it equation 1 and let's call it equation 2. So from equation 2, if we put the epsilon naught epsilon r epsilon naught a divided by d minus y whole square into v square whole term as ky, then we can write is, so from 1 and 2 can write, so what I am writing, epsilon r epsilon naught a v square divided by d minus y whole square. So this is equation 1 I am rewriting just in different form into d minus y, right. So d minus y whole cube I just separated d minus y square into d minus y minus k less than 0. Now this term is 2ky, right. So 2ky divided by d minus y minus k less than 0, right, or 2ky divided by d minus y less than k, or 2y less than d minus y, or y so this is actually less or equal to d by 3. Okay. So it means that for a deflection of the 1/3 of the gap, the beam will be in stable condition, and after that the beam will pull in on the bottom plate, right. So this is what we get, and remember this D is the initial gap between the two plates. Okay. Now what is the pull-in voltage? Pull-in voltage we can calculate like this. So we know that if the Y is the deflection, then the electrostatic force half epsilon r epsilon naught A divided by D minus Y whole square into V square, right. This is the electrostatic force is equals to Ky. So this is Vp, because at pull-in voltage these two terms are same, and at pull-in condition, what is the limiting condition for pull-in? That is Y equal to d by 3. So let us put this Y equal to d by 3. So then we get epsilon r epsilon naught A divided by d minus d by 3, right, whole square Vp square is equal to K into again d by 3, right, and we will get that half into epsilon r epsilon naught A divided by 2d by 3 whole square, right, 2d by 3 whole square, 2d by 3 whole square into Vp square is equal to Kd by 3 is equal to Kd by 3. Okay. Now we take this thing up, so it becomes, so 3 square 9, that goes to the top, this 3 also comes here, so this becomes 27, right, and then this is 2 square 4, so 4 into 2 8, 27 by 8, right, into epsilon r epsilon naught A divided by, let us say this is d square, and we take this d also, so d cube, right, into Vp square is equal to K, right. So Vp square is equals to 8 K d cube divided by 27 epsilon r epsilon naught A. Okay. So Vp is equal to square root of 8k d cube divided by 27 epsilon naught A. Fine. So this is my pull-in voltage in terms of the beam geometry. So to see now the pulling phenomena, I will describe this with the help of this example. Okay. So there we have taken this kind of structure where we have the substrate, and on top of the like this substrate can be silicon or glass, and then on top of that there is an insulating layer which is let us say SiO2, and on top of that there is a cantilever beam. Now this cantilever beam is like the metal electrode, is like the plate A which we discussed earlier, like the top plate, and at the bottom also there is a electrode, there is an electrode which is also let us say made of silicon or polysilicon, and then metal deposited on that. So these two, top electrode and bottom electrode, are electrically disconnected from the sample because this is on a substrate. this is on a SiO2 layer which is insulating. So these are not connected electrically. The electrical voltage phi is applied from the a battery externally. Okay, and now let's consider that the overlapping area of these two electrodes are the length is about 300 micron and the width is about 5 micron. Okay, and the gap between plate A and plate B is 1 micron. Now we already know this expression, that is K for this cantilever beam, the stiffness constant of this cantilever beam, which we can get from the mechanics. What we need to say, what we need to find out, we need to find out the pull-in voltage and also the how much gap it can deflect, how much it can deflect without actually pulled in on the substrate. From our earlier analysis, we know that the electrostatic force in this case will be half of epsilon r epsilon naught into A, right. So let's consider in between these two plates there is air, so no epsilon r, only epsilon naught. Okay, and that becomes epsilon naught A divided by d minus y whole square, earlier we wrote, right, and here in this case it will be, let's call it gap G0 minus uz. So I am considering the deflection, considering here the deflection in this direction is uz. Okay, is positive uz. So you at the, while the beam is not deflected, uz is 0, and while the beam is completely on the plate like the bottom plate, then uz is equal to G0. Into phi square, right, and at pull-in condition the electrostatic force and the mechanical force will be same, right, minus K into uz is equals to 0, right, and then we can simplify it to this expression uz cube minus 2 G0 uz square plus uz G0 square minus epsilon naught A phi square divided by 2K equals to 0, and then we can write down all the values as we already know. Okay. So it becomes uz cube minus 2 into G0, G0 is the gap which is 1 micron, so that is 10 to the power minus 6 into uz is our unknown variable plus uz to G0 square means 10 to the power minus 12 minus, so A we already know, A is 300 into 300 micron into 5 micron, that is 1500 micrometer square, right. Epsilon naught also we know, that is our air permittivity. So let me write down the epsilon naught value. Epsilon naught value is 8.85 into 10 to the power minus 12 farad per meter, okay, in SI unit. So now we put all those values, K also we know, right. So if we put all those values, then we get, it will come as 1.17 0.06 into 10 to the power minus 19 into 5 square is equals to 0. Okay. Now important point to note in this equation is uz is a it has cubic power, right? It is a power of 3. So this is a cubic equation, and that means it can have 3 roots, correct? And as all the other terms are known, only the unknown value is the phi, and putting different values of phi we can get different solution of uz, right? So let us put phi different values. Let us say this is my phi, and then I will have 3 root, right? So this is, let us say, uz1, then I have uz2, and then I have uz3, right? If phi is equal to 0.5 volt, the first case, let us see that what happens if phi is equal to 0. Phi equal to 0, then one root will be 0 and other two root will be 1 1, right? And that you can see from this equation also. If you put phi equal to 0, then it becomes like uz cube minus 2 into 10 to the power minus 6 uz square plus uz into 10 to the minus 12 equal to 0. So uz goes out, so you get uz equal to 0 1 root and uz minus 1 micrometer as another root. So you get 0 1 1, okay, and these all are in micrometer. All are in micrometer. So this will be 0 0 for 0 voltage, one root will be 0 and other two roots will be 1. Now what happens for 0.5 volt? For 0.5 volt, the roots will be 0.031, 0.81 and 1.15. Now see, in this voltage combination, all the 3 roots I have got. Now here this 0.031 micrometer is possible because this is below 1 micrometer. This is also, second root also is possible, but the third root is 1.15 micrometer. Now as the gap itself is 1 micrometer, 1.15 micrometer deflection is not possible. But so this is one of the impossible roots. But mathematically you cannot actually avoid this root, but from physical interpretation you know that more than 1 micron deflection is not possible because the gap itself is 1 micron, right? But while I am putting it into this equation, we are not considering that is the maximum value of uz, right? So you can get that root, and this is the root A, like in this diagram, in this graph. Let's go back. Is root the first root is like this A point and the second root is like B point, right? Okay. Now take another voltage, 1.125 volt, 1.125 volt, and in that case you will see that the two roots will be 333 like this, right? And the second root also will be like this, 0.33, and the third root will be 1.333. So here the third root is definitely not possible, but the first two roots are possible, and this is the case where actually y is equal to, or the uz is equal to gap by 3, because gap is 1 micron, right? And in this case we are getting both the roots as gap by 3 or g0 by 3. So this is, we go back to the, so this is this case like V3 or my Vp. So from now on, from this root itself we can say that this Vp is 1.125, but anyway we will actually derive that also. But this is this case, right, where the voltage is Vp or equal to the pull-in voltage, and it is exactly touching at this point. So both the roots are merging at 0.3333, and then the third root is anyway impossible root. Now take, let's say, more voltage than that, then we, if you take 1.5 volt, we get this is also imaginary 1.429. So if we take more voltage than pull-in voltage, then already we know that there is no stable condition, means there is no point where the electrostatic force and the mechanical force can be same. So we get the imaginary root, and another root is more than 1 micron gap, which is also not possible. So there is no possible solution for the case where it is more than the pull-in voltage or while the gap is more than 0.333. So now we will calculate the pull-in voltage, and for pull-in voltage we already know from this expression, already know that for y will be, or the deflection will be less or equal to gap by the 3 or 1/3 of the gap, right. And then if we write here, then we can write that at pull-in condition uz is equal to g0 by 3 or equal to 1 by 3 micron. This is 0.333 micron, right. And in that case we know that Vp or phi pull in is equals to square root of 8k g0 cube divided by 27 epsilon a, right. And here if we put all the values, because epsilon naught we already know, and then a is 1500 micrometer square, g0 is 1 micron, and k is already given, k is given as 0.057 Newton per meter, and if we put all those values, then we will get phi pull in is equal to 5 volt, 1.125 volt. So before going to the next topic, we will revisit once the transverse displacement case, where we have seen that if the two plates are moved parallel to each other, like top plate and the bottom plate, so one plate is fixed and another plate is moved, okay, in transverse direction, then the overlapping area actually changes, and there we saw that the transverse force is equal to B into epsilon r epsilon naught divided by 2d into v square, where this B is the width of the plate and d is the distance between them, and v is the applied potential, and epsilon are the permittivity. Now this concept we need for our next case, which is a comb actuator. So what is a comb actuator? Comb actuator is a structure like this. So I will draw the structure. So this plate is fixed at these two supports. So this shaded region at the points where the beam is fixed. Now there are some comb kind of structures connected the both side of the proof mass, right, and these are like fingers, and then we have some static fingers also. So similar kind of structure is present on the other side also. So this mass M can move in x and y both the direction, okay, and the voltage is applied between the static combs and the moving combs. So, these combs which are connected to the proof mass are the moving combs, right, these combs, and the other combs which are connected to this static plate cannot move. Now, if we apply a potential difference between the static comb and the moving comb, what will happen? Because of the electrostatic attraction, it will pull the device or the actuator towards it, right, and the force F will be equals to B into epsilon r epsilon naught divided by d v square, and that is, this is for only one pair, right, and there are, let us say, n number of combs. So, it will be n b epsilon r epsilon naught divided by d into v square, and here the important thing is that this is v, potential. Important thing is this b is the width of each comb, means it is out of the plane, like in the paper, out of the plane displacement. Here the beam, this b is the width of the beam, means if this is the comb, and if this is moving in between the other two combs like this, then this b is this width, right, which is perpendicular to the plane of the paper, because I am drawing it like this. This is the plane of the paper, and I am drawing on this, right, and this is the comb, which is the static comb, and then this structure or the moving combs are coming towards it and going away from it like this, right. So, this b is the width which is actually perpendicular to the plane of the paper, right, this width. So, important point to note from this expression is that the force is only dependent on the velocity square. This n is the number of comb, this b is the like width of the beam, which is also like beam geometry only, epsilon is material property, and then d is the gap between each comb, and that is also geometry, that also fixed and comes from the geometry. So, there is no dependency on the how much the beam has, how much the combs have moved, right. So, we can decide the force, but by just changing the voltage or this V, right. And again, if we know this, these are the two fixed points, and for these beams, if we know the stiffness constant, then for displacement, let us say in x direction, we can write that this is, so this is transverse force is equal to transverse stiffness constant into, let us say, x, which is the displacement. So, accordingly, so whatever displacement or whatever movement we want for the proof mass, that we can implement by just changing the voltage, okay. And another point to note is that these combs, the static combs and the movable combs, are arranged such that there is no force, no resultant force in the y direction. So, in this direction no force, so that is F normal, or the normal force, is equals to 0. So, there will be no movement in the y direction, only the x direction movement will be there, and that we can control by applying the external voltage, and this is called comb actuator. This is a kind of device where we can actuate it by applying some electrical voltage according to our requirement. So, we have already seen this structure, right, where two plates are there, the bottom plate is fixed and the top plate is moving, and you can apply some potential V. Let us say that plate was initially here, the actual distance between the plates while it is not deflected, it is d, and then the deflection is taken in this direction, it is y, right, deflection is y. Okay. Now this kind of structure also can be used as variable capacitor. How? If we apply different potential, then the top electrode will be attracted towards the bottom electrode, and accordingly with different kind of potential we can make it stable at different position. As we have seen that for different kind of voltages, as we apply, we have seen that for different kind of voltages we get different routes, right, we get different possible routes, and there we can actually make the cantilever or the top plate stable at different position. Now if the cantilever is stable at some position, then if we measure the capacitance in between those plates, then it is different from its earlier position, right, because capacitance C is equal to epsilon A by D, like the parallel plate capacitor formula, where A is the area of the two plates and D is the gap between the two plates, right. And here C is equal to, at any position where y is equal to, where the deflection is y, we can write it as, let us assume only air is there, epsilon A by D minus y, right. Now because of the external circuitry there is some stray capacitance also, so let us call that stray capacitance Cs. So this is because of the external circuitry, because of the contacts and everything else, okay. And the device capacitance, so this is the device capacitance CD, okay, this is the device capacitance CD, okay. So this let us not call it D because our main gap is D. Whatever is the gap between G, whatever is the gap at that position while it is deflected by Y, so that is D minus Y, right, okay. Now the total capacitance is equal to C equal to Cs plus C of device, it is stray capacitance plus the device capacitance. Now this Cs is from the external circuitry, so this cannot change anyway, but this device capacitance can change because of the different gap or different Y. Now what is the minimum value of device capacitance? CD mean is equals to epsilon naught A by D, right, because Y can be 0, deflection can be 0 while it is not at all deflected. So this is the CD min, right, while what is the CD max? So that we know from our pulling phenomena, because from our pulling phenomena we know that it can the gap maximum can be D by 3 without snapping on the substrate, right, because after that if the gap is more than D by 3 like lesser than D by 3, then the top plate will snap onto the bottom plate, right. So CD max will be epsilon naught A D minus Y, or maximum value of Y, and that is D by 3. So that is 3 by 2 into epsilon naught A by D, right, and from that we can also write that CD max divided by CD mean is equals to 3 by 2, right. So we can actually apply different voltages and can make the top plate stable at different position, and accordingly can change the capacitance of these two parallel plate, and this is called variable capacitor.